Harry Potter, come to die. I'm running out of nerd intros, so if you have any requests, feel free to send them along the way. And if you ever wonder why, just remember, because science. All right. Well, today we're going to talk about the mechanisms of glycolysis and also of the pyruvate dehydrogenase complex. And this is going to take us all the way from how your body deals with glucose and breaks it down all the way into a molecule called acetyl-CoA, which is going to be the entry point into the citric acid cycle. And I'll just point out at the beginning here that the things that we're talking about are not covered in a lot of detail, if any, in your text. And so you're going to have to rely on the lecture notes. Many of you have asked about study guides, and it turns out the best study guide I could really give you for this section of the class is just the lecture notes, which I post anyway. And if you have questions about specific reactions or specific mechanisms, it turns out Wikipedia is a decent source for this sort of thing, but you can always email me your questions and I can try to answer them in a little bit more detail. All right. The other thing I wanted to say is you'll see right away when we start looking at the notability that I've already pre-drawn a lot of the large biomacromolecules, or rather a lot of the molecules that are bigger like ATP and ADH. I do that to make the video shorter. I feel like it's still a good idea for you guys to be following along at home and taking notes. If you need to pause the video, you can to get a structure down. And hey, that's something you could never do in class, so yay. All right, with that, we'll turn to notability. I think my nose was red in that shot because of that stupid Voldemort mask. All right, so as we mentioned last time, glycolysis will metabolize glucose into 2 molecules of pyruvate, and in the process we'll get 2 molecules of ATP and 2 of NADH. So this process is quite long, but it's not very high yielding in terms of molecules with high energy bonds in them. A couple other things to sort of state at the outset. You may have learned in previous classes that ATP releases energy when bonds are broken. That is not true. As you learned in 351, breaking bonds always requires you to put in energy. It's only when new bonds are made that are more stable than the ones you broke that a reaction releases energy. And so we'll see that even in our first step of glycolysis. There's another misconception in terms of how your body uses ATP to do work, and we may talk about that at the end, but for today we'll focus on the mechanisms of glycolysis. So in the first few reactions, we're investing high energy molecules in the process. So we're actually going to consume a couple molecules of ATP, and we need to do that in effect to supercharge our glucose molecule so that the rest of the reactions can proceed without a lot of trouble. In our first reaction, we're going to take glucose. Here's the 6 carbons of glucose in its cyclic hemiacetal form. I've used the squiggly line here for the anomeric OH group, or rather the hydroxyl attached to anomeric carbon number 1, to indicate that you probably have a mixture of alpha and beta anomers. Over to the right, I have a molecule of ATP. You'll recognize this from the last lecture. This is the adenine portion, the ribose portion. Together that's adenosine, and then the TP stands for triphosphate. Notice that the alpha and beta phosphates are negatively charged oxygens on those groups are chelated to a magnesium 2 plus ion, which will end up making ADP a better leaving group. The enzyme that catalyzes this reaction, and I'd like you to know this, is called hexokinase. Kinase in general is the term we use for enzymes that use ATP to transfer a phosphate group onto something else. And then the hexo part tells you that this kinase acts as on a hexose, like glucose. And the product of this reaction is, well, when the reaction happens, we're going to see the gamma phosphoryl group from ATP transferred onto the C6 hydroxyl group, right? The hydroxyl group bonded to carbon 6. So we're going to transfer that phosphoryl group from ATP to the hydroxyl on carbon 6. And if you look at the bonds we break versus the bonds we form, it's kind of interesting. So we're going to zoom in briefly on ATP. The bond we break is actually right here. It's the bond between the gamma phosphorus and the previous oxygen. And that kind of bond is called a pyrophosphate bond, but it's also called a phosphoanhydride. And I can't remember whether I mentioned this in the last lecture or not, but phosphoanhydrides are similar in stability or are analogous to carboxylic acid anhydrides. So if you remember back to chapter 22, we encountered a molecule like this, and we said that the two carbonyl carbons are identical, so we'll just choose one of them. That carbonyl carbon is very reactive because it's attached to something that is a good leaving group. If acetate leaves, the negative charge is stabilized by resonance. You can tell that it's a decent leaving group because the conjugate acid of the acetate leaving group is acetic acid, which is a decently strong acid, pKa around 4. All right, so we will see, we saw previously that anhydrides could do substitution chemistry in the presence of a nucleophile. And when that nucleophile was, say, an alcohol, you could convert the anhydride, and here's the acetate leaving group, you could convert the anhydride into the ester. And we said that esters were more stable than anhydrides, and the rationale for that was that the oxygen in the anhydride is not as good of a resonance donor as the oxygen in the ester, because the oxygen in the anhydride in between the two carbonyls can donate its electrons to either carbonyl group, so its impact is sort of split, whereas in the ester, these electrons on the oxygen can only donate electron density into the carbonyl carbon. And the other reason we know that esters are more stable than anhydrides is just the fact that the potential leaving group on the ester, OR minus, is a much less stable leaving group than the carboxylate group. So, by analogy, phosphoanhydrides are similarly reactive, And one of the reasons for this is that what's attached, if we have some nucleophile come in, the thing that would leave ADP is a good leaving group. The negatively charged oxygen would be stabilized by resonance, to say nothing of the magnesium 2+ ion that's also stabilizing the negative charge. So as we discussed last time, sorry about that, the mechanism for transfer of a phosphate group is going to be basically SN2-like. We're going to show the oxygen on carbon 6 attacking the gamma phosphoryl group, and we'll see the leaving group leaving. We probably need to have a base remove a proton from that C6 hydroxyl group, whether that's probably from the enzyme or solvent, and whether it happens before, during, or after attack, we don't really care about at this point. So I'm just going to draw it all in the same step. Base removes a proton, the oxygen becomes negatively charged and then attacks the gamma phosphate. And then we're going to break the pyrophosphate bond, and electrons from that bond are going to go onto that oxygen. And that's going to give us our glucose 6-phosphate and a molecule of ADP. Now, if we look at the product of this reaction, in the same way that if we took an alcohol and reacted it with a carbon anhydride, we would get an ester. When we react an alcohol with a phosphoanhydride, what we get is a phosphoester. And just as esters are more stable than anhydrides, where do I want to put this? Phosphoesters are more stable than phosphoanhydrides. Run out of space to write phosphoanhydride. Phosphoesters are more stable than phosphoanhydrides. And you can tell that that's the case by looking at this free energy difference. This very large free energy difference between starting materials and products. We're going downhill in energy by about 8.1 kcals per mole. You'll see different numbers quoted all over the place. This is a number that reflects the realistic concentrations of starting material and product in the cell. And so it's a reasonable estimate of how downhill in energy this reaction actually is. Remember that in organic chemistry, changes that are worth 1.4 kcals per mole change the equilibrium constant by a factor of 10. So that when we have a delta G of minus 8.1 kcals per mole, you're looking at a factor somewhere between 10 to the 4, 10 to the 5th in terms of equilibrium constant favoring products over starting material. So the reaction is basically irreversible. There are 3 steps of glycolysis that are irreversible. This is one of them. Each of them involve making a much more stable bond or bonds than the ones that you broke. And each of them, because they're irreversible, if a starting material goes through it, you've committed to the process, and therefore these steps are highly regulated, and you'll learn more about that in biochemistry. So we've made a phosphoester. Let's move on to the second step. So the second step is catalyzed by an enzyme called glucose 6-phosphate isomerase. Enzymes are generally named according to what they do, so you might expect this isomerizes glucose. So let's look at what's changed. We have glucose 6-phosphate here. That's simply the product of our previous step. And we're going to rearrange it to become fructose 6-phosphate. We maybe didn't talk about this very much in the carbohydrates chapter, but glucose and fructose are the two individual sugar components, carbohydrate components of table sugar. Glucose can be interconverted with fructose via a simple tautomerization mechanism. They are isomers of each other. They basically differ in the location of a carbon-oxygen pi bond and a couple of protons. This step is very reversible. The free energy change from glucose 6-phosphate to fructose 6-phosphate is hardly worth noting at all. One of the things you can notice here, and you can tell the difference between the two, is in glucose, the C5 hydroxyl group here, this oxygen on the corner that I'm trying to point to, is bonded to anomeric carbon number 1. In contrast, in fructose, that same C5 hydroxyl group is bonded to anomeric carbon 2. So we've changed where the anomeric carbon is, and that's allowed us to go from something that was a 6-membered ring to something that's a 5-membered ring. The mechanism here, as I said, is tautomerization, basically proton transfers, and we're going to see that there is a key ene-diol intermediate where we can go either way, back to glucose 6-phosphate or on to fructose 6-phosphate. The first step of this mechanism is going to be opening of the cyclic hemiacetal. We could show this in multiple steps. I don't necessarily think we need to, since you should be pretty good at drawing hemiacetal hydrolysis mechanisms. So a base removes a proton from the C1 hydroxyl group. These electrons kick down to the anomeric carbon to restore the carbon-oxygen pi bond, and then the electrons between the C5 hydroxyl and anomeric carbon 1 move out onto the oxygen, and probably at the same time that oxygen gets protonated from somebody, either a solvent or an enzyme, or perhaps even the conjugate acid of the base here that did the initial deprotonating. So this is an acid-base step. It may help you if at this stage I continue to draw glucose in this sort of chair-like orientation. I will sometimes abbreviate a phosphate group with OPO3 2-. Hopefully that's not too confusing. We'll keep the OH groups in the same spot. Only on carbon 1 now we have an aldehyde. And it may help us through the process to continue numbering these carbons. Alternatively, you may find it easier to draw this out in its sort of straight chain form. So to do that, we need the phosphate group on the one end. 1, 2, 3, 4, 5, 6. And then we just need to make sure that the OH groups 1, 2, 3, 4, 5, 6 are in the right place with the right stereochemistry. You've kind of done a problem like this before on a previous exam. where you had to get the stereochemistry right. So let's see, up, up. All right, so that's the open chain form of glucose 6-phosphate. So one of the interesting patterns here that you might come to recognize is that glucose 6-phosphate is an alpha hydroxy carbonyl compound. Here's the carbonyl compound, here's the alpha carbon. And what we're going to show you, this tautomerization process that's actually going to move the carbon-oxygen pi bond from carbon 1 over to carbon 2, is possible anytime you have an alpha hydroxy carbonyl compound. So the first step is for us to remove the alpha proton, and that's going to generate an enolate. The negative charge would be delocalized on both the alpha carbon and on the carbonyl oxygen. And we could show that enolate as an intermediate, but it might be easier for us to simply show that enolate getting protonated directly on the carbonyl oxygen. If you want to pause and show that, oh heck, I guess I have copy and paste capability, and I'm concerned that some of you are going to get a little bit mixed up if we condense all of that into the same step. So we'll go ahead and make the enolate. Then we'll show that resulting enolate getting protonated on the carbonyl oxygen. So electrons kick down here to form a pi bond, and then we pick up a proton from some acid, perhaps the conjugate acid of our base. And that will give us a key important intermediate, which I referred to when describing the mechanism. We'll need to erase some things so the changes are clear. We should have a new oxygen-hydrogen bond here. Oops, let's just put the OH there. We should have a new pi bond between carbons 1 and 2. And then this OH group that was up, now because carbon 2 is in a pi bond, it's sp2 hybridized, that OH group has to be in the plane of the pi bonds. And I've shown the two OH groups trans to each other. I'm not actually sure whether it's known if they're trans or cis. It doesn't matter, so if it's okay, we just won't worry about it. Then, to generate the, to get to the fructose, hold on, let me just point out this is our diol intermediate. And the interesting thing about the diol intermediate is that it's an enol in both directions. So the pink enol has carbonyl carbon here and alpha carbon there on carbon 2. In contrast, the blue enol has carbonyl carbon at 2 and alpha carbon at 1. So we could tautomerize this enediol and together these two proton transfer steps did a tautomerization. We moved the location of a pi bond and a proton. But the interesting thing about the enediol intermediate, as I said, is it's two enediols rolled, it's two enols rolled up into one, and it's very easy to switch and make the new pi bond between blue oxygen and blue carbon rather than between pink oxygen and pink carbon. So let's show you how that mechanism works. We'll have some base remove a proton from the blue oxygen. You might ask, why doesn't it remove a proton from the pink oxygen? And I will say it can and does, and that would be going backwards. But to go forward, oh, we've got laser pointer functionality. That is so useful. I'm very excited about that. I didn't see that. Okay, man, don't have to use that big clunky square thing anymore. So let me show you the enolate that comes from removing the proton from the blue oxygen. I'll erase the pink stuff. There should be a negative charge on our C2 oxygen. And we can now protonate this enolate on blue alpha carbon 1 by kicking these electrons down and then protonating on the alpha carbon using some acid, perhaps from the enzyme and perhaps the conjugate acid of our base. Notice what that does. I realize we're sort of running out of space. Let me move over our friend fructose. Oops, 6-phosphate. Didn't want to move the gray line. All right. Let's see. All right, we'll zoom in. When we protonate on blue alpha carbon 1 and make a new pi bond between carbon 2 and its oxygen, we have basically moved the carbonyl over. We started out with an aldehyde. We did a series of tautomerization steps to get to the enediol, and then we did tautomerize again to get to the ketone. And now closing up to the 5-membered ring hemiacetal is as simple as having a base remove a proton from the C5 hydroxyl group and then have that attack the carbonyl carbon. At the same time, we protonate on the carbonyl oxygen, and that will get us to our fructose 6-phosphate intermediate. All right, I'm going to pause just a second while you're getting some of that down and while I'm trying to make it look prettier. All right, that'll do. Okay. So if we were to go through and review this mechanism again, you start out with something that is a cyclic hemiacetal. Then you do the ring opening acetal ring opening of the cyclic hemiacetal via those two proton transfer steps. And the product that you get is this aldehyde. Remember, glucose is, an aldehyde, which, as we discussed, is why having high blood sugar levels is a bad idea. And so these first two steps that we noticed over here, where we remove the proton from the alpha carbon and then protonate on the carbonyl oxygen, we're going to call that tautomerization. We're going from keto form to enol form. But we noticed that our intermediate is actually an enol in both directions. And so if we remove the proton from the C2 hydroxyl group, we get a second enolate. We get a second enolate. And if we protonate on blue alpha carbon C1, then we get the ketone open chain form of fructose. So, these two steps are also tautomerization steps. Oops. I wonder if I can rotate that a little bit and shrink it. It works. And once we get to the ketone, we can do ring closing hemiacetal formation to get a cyclic hemiacetal form of fructose 6-phosphate. And this is the furanose form because it's a 5-membered ring, whereas up here it was a pyranose form. Okay, so simple tautomerization reactions get us from glucose 6-phosphate to fructose 6-phosphate. The next step is actually going to be to install another phosphate ester on the C1 hydroxyl group. So we're going to go from fructose 6-phosphate to fructose 1,6-bisphosphate, one phosphoester on the C1 hydroxyl, one phosphoester on the C6 hydroxyl. And goodness me, we've discovered an error in the drawing of fructose. Some of you were probably yelling along at home. You guys are probably too old or too young. I don't know. I'm not sure whether you remember Elmo's World or not, but there used to be a section in Elmo's World where goofy Mr. Noodle would appear in the mirror and get everything wrong. So you guys may have been at home screaming along, "You're missing an oxygen, Mr. Noodle." I'm not sure why you'd want a creepy guy in your house, in the window of your house looking at stuff, but there you go. It's getting weird. All right, so that's fructose 6-phosphate. It looks like I need to correct that structure there. And we're going to install a phosphoester on carbon 1. We're going to do this using another equivalent of ATP. So this is the second molecule of ATP we have donated to this purpose. The enzyme that catalyzes this is also called a kinase, phosphofructokinase. This is another of the irreversible steps in glycolysis. It's downhill in energy. And the reason, of course, is because you are replacing a phospho and hydride bond with a more stable phosphoester bond. So this is not quite as downhill in energy as the first step, but it's a high enough, it's a large enough change in free energy that you expect equilibrium constant to favor products by close to a factor of 1,000. And of course we get ADP as our leaving group. The mechanism is the same one we've seen before, SN2. All right, so we now have phosphate groups on either end. That's deliberate because in the next step, we're going to split this molecule up into 2 3-carbon pieces. And poor silly me has missed. This is what happens when you make copy and paste errors. They propagate themselves through the rest of your document. All right, there's the C6 hydroxyl group. That is a phosphoester. So in step 4, we're going to first open up the fructose 1,6 bisphosphate cyclic hemiacetal. And then we're going to split the resulting 6-carbon chain into 2 3-carbon pieces. One will be called glyceraldehyde 3-phosphate, and the other will be called dihydroxyacetone phosphate. Glyceraldehyde 3-phosphate comes from carbons 4, 5, and 6 of fructose, and dihydroxyacetone phosphate comes from carbons 1, 2, and 3, except I got the order wrong. It should be 1, 2, 3. All right. So first step is going to be hemiacetal ring opening. I already showed you how to do that before, so I won't repeat it here. And we'll draw the ring opened form of fructose and then we'll just need to modify our drawing just a little bit so that we have everything in the right place. I'm gonna just put the oxygen here and abbreviate the phosphoester portion of our molecule. All right, so we went from the cyclic hemiacetal form to the open chain ketone form. And now I want you to look at this, the structure of the open chain form. And I believe we talked about this a couple weeks ago back in chapter 24. But one of the structural patterns that you were taught to look for, well, there were a couple of different carbonyl sort of structural patterns you were taught to look for. You were taught that if you see a beta ketoester, you could have made that through a Claisen reaction. That if you saw an alpha beta unsaturated carbonyl compound, you could have made that through an aldol reaction. Or if you had a beta hydroxy alcohol, you could have made that through the aldol reaction. And I want you to pay attention because embedded in this molecule, we definitely have a beta hydroxy ketone. And this is an aldol product. Now, as we said back in chapter 24, aldol reactions are reversible and can go backwards. Retroaldol is possible. So let's think about, if we were going to do a retroaldol reaction, what that might look like. Recall from chapter 24 that when you see the beta hydroxy carbonyl compound, it's this bond between alpha and beta carbons is the one that you made during the aldol reaction. So let's imagine what the previous intermediates would have been. So we start with the beta hydroxy ketone. Do you remember in the aldol reaction how we got that beta hydroxy group there? Go ahead and think about it. Pause the video and look it up. Now that you've done that, hopefully you remember that immediately before we get the beta hydroxy carbonyl compound, we encounter its conjugate base with the negatively charged oxygen on the beta carbon. And this is what you get when an enolate attacks a carbonyl compound. So this side, carbons 1, 2, and 3, would have been our enolate. And then this side, carbons 4, 5, and 6, would have been our aldehyde. So let's just imagine what that would look like. And that's carbons 4, 5, and 6. And then, of course, over here, we would have an enolate and we could very easily have gotten that from its corresponding conjugate base. So this molecule here is glyceraldehyde 3-phosphate. This molecule here is dihydroxyacetone phosphate. 1, 2, 3, 2, 3. All right, so let's show how those arrows would work. It looks like to get from the beta hydroxy carbonyl compound to its negatively charged product, we would need some base to remove the proton, and that would get us to the alkoxide. This is basically the tetrahedral intermediate, and this portion on the left is going to have been our enolate, and this portion, oh my gosh, I just got left and wrong, right? Incorrect. Left and wrong. This is going great. I got left and right mixed up. So over here on the right, you have the enolate. Over here on the left, you have what would have been the aldehyde, which now that I've corrected myself, we can put there. It's the bond between carbons 3 and 4 that we're going to break. And we do that as electrons on the negatively charged oxygen kick down and break this bond between 3 and 4 with the electrons going to carbon 3. That then forms an enolate, which can be protonated by some acid, perhaps from the enzyme, perhaps the conjugate acid of a base that we've used previously, and that gives us our two products, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. All right. It's worth pausing here to think about the chemical strategy that led us to this point, where we could split a 6-carbon molecule up into 2 3-carbon molecules. And to deal with this, we're going to scroll upward to look at the open chain form of glucose. And I want you to notice that glucose is a beta hydroxy carbonyl compound as well. And so I want you to think about, what if we did the backwards aldol reaction at this stage with glucose 6-phosphate? What would that have done? So I want you to think about what bond we would have broken if we did a retroaldol reaction from this beta hydroxycarbonyl compound. It's the bond between alpha and beta carbons, right? So if we did the retroaldol reaction, we would break this bond. Carbon 3 would be an aldehyde. Carbon 2 would have a negatively charged, it would be negatively charged. It would be an enolate, which would get protonated. But you would have split this up into a 2-carbon piece and a 4-carbon piece, which may not seem so bad, but if you think about it, something with 4 carbons is a lot bigger and different in shape than something with 2 carbons. And if we had done that, nature would have needed to evolve 2 separate sets of enzymes for dealing with the 4-carbon subunit and the 2-carbon subunit. Instead, nature chose to move the carbonyl group over via tautomerization reactions, so that now the beta hydroxycarbonyl group could be in a position where, if we broke it apart via an aldol, a retroaldol reaction, we would break the molecule into 2 even pieces. And it gets better than that. Right now it looks like we still have 2 different molecules, but in the next step we're going to use the same type of tautomerization via an ene-diol intermediate to convert dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. I'm going to leave it to you to draw that mechanism. I will draw for you the ene-diol intermediate, and then I want you to push arrows to do the tautomerization steps that get you to the ene-diol intermediate. And then I want you to do the tautomerization steps that get you from the ene-diol intermediate to the desired product. But again, the key feature here is that you have one enol here with its carbonyl carbon and alpha carbon, and then you have another enol here with its carbonyl carbon and alpha carbon. And so that ene-diol intermediate allows you to interchange freely between dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. So now, if you look at what we have done, for each glucose molecule, we now have 1, 2 molecules of glyceraldehyde 3-phosphate. So now we've broken glucose into 2 smaller pieces, but the 2 smaller pieces are exactly the same thing. It's really beautiful how that works out in this case. An elegant solution to the problem of how to break glucose down into pieces that we can use to generate some high energy molecules like ATP and NADH. All right, so we've got 1 and then 2 glyceraldehyde 3-phosphates. So the remaining reactions, everything we do from this point on, is going to be payoff. So let me just look into how many of the steps we need to go through. All right, it's not too long. I think we'll continue on. I realize we've moved past the 50-minute point, but I think it would be better just to forge ahead. And if you want to pause and come back to this a little bit later, you're welcome to do that. This is the payoff phase. Everything from here on happens twice, and we're going to start generating energy-rich molecules, high-energy molecules that we can use to do other reactions. So in this reaction, this is kind of a interesting and confusing one. In this reaction, we're going to have glyceraldehyde 3-phosphate react with a molecule of inorganic phosphate to generate 1,3-bisphosphoglycerate, and in the process we're going to oxidize the aldehyde to a mixed anhydride. This is like an anhydride that's a hybrid between a carbon anhydride and a phosphoanhydride. The group on one side is a carbonyl carbon. There's the oxygen. The group on the other side is the phosphate group. So this will necessarily involve oxidation from the aldehyde oxidation state to the carboxylic acid oxidation state. And because of this, we're going to use an equivalent of NAD plus to do the oxidation, and that will give us NADH as the product. The enzyme that catalyzes this reaction is called glyceraldehyde 3-phosphate dehydrogenase. You can tell a lot of the reactions that do redox chemistry because many of them are named dehydrogenases. And one of the reasons they're sort of called this is because they involve losing basically the equivalent of hydrogen, H2, from a molecule. All right, the free energy change in this reaction is negligible. The reaction's reversible. The mechanism, we're going to need to probably insert a page at this point. All right. In the mechanism, we're going to take glyceraldehyde 3-phosphate and the HPO3 2-, and we're going to do addition to a carbonyl type chemistry. So lone pairs on the phosphate group attack the carbonyl carbon to generate a tetrahedral intermediate. That oxygen probably gets protonated at some point, or I suppose you might consider that it's negatively charged and maybe it fits into some pocket where there's hydrogen bonding, so maybe you don't need to completely protonate it. The intermediate there, and I'm going to start abbreviating things to only show the relevant parts of the structure. So let's see, sorry, this step is just addition of a nucleophile to an aldehyde. What you have here is the tetrahedral intermediate. Here's the hydrogen, and here's the phosphate group that we just barely added. And you'll recall back in chapter 20 when we did addition of nucleophiles to aldehydes, we would often get to this point and say, well, if there's a good leaving group, it can get kicked back off, and that can certainly happen. These electrons could kick off the phosphate as a leaving group. And we wouldn't normally have thought of this hydride as a good leaving group because it's not, but the enzyme places this hydride very close to the nicotinamide ring of NAD+. And recall that we can draw a resonance structure for this nicotinamide ring of NAD+, in which the nitrogen is neutral, but we have a positive charge on carbon 4. So carbon 4 is really the electrophilic spot in this molecule. We're going to have lone pair electrons kick down, and hydride will leave and be handed off directly to carbon 4 of NAD+. And that will generate the products we've shown below. You can push the arrows from either mechanism here. If you're doing the one on the right, you only need one arrow. Here, over here on the left, you would need these two arrows to get you to the desired products. And I'm not going to draw them again because they're written above. All right. What do you suppose we're doing here? Why do you suppose that we have now attached a phosphate group to a carboxylate group via a mixed anhydride? What do we know about anhydrides? Well, anhydrides are very reactive. They have high energy, low stability bonds. And we're going to need that because we're going to use 1,3-bisphosphoglycerate to convert ADP into ATP. So here is our next reaction. 1,3-bisphosphoglycerate reacts with ADP to generate ATP and 3-phosphoglycerate. Now look at the delta G there. It's basically zero. This reaction's fully reversible, and the reason it's fully reversible is that you are replacing an unstable mixed anhydride with an unstable phosphoanhydride. So the bonds that we made are just about as stable as the bonds that we broke. Overall, no huge change in free energy while recharging ADP to ATP. This is really miraculous. The idea that you could recycle and convert ADP back into ATP without a change in free energy is remarkable, and it has to do with the fact that we've used the investment phase of our glycolysis to get to the point where we were able to make a high energy molecule from a lower energy molecule. I'm sorry, make a high energy molecule from glyceraldehyde 3-phosphate coupled with reducing NAD plus to NADH. All right. So the mechanism here is just SN2. You could show lone pair electrons on the beta phosphoryl group attacking this phosphorus and leaving group leaves to give you the gamma phosphoryl group of ATP. Now remember, this happens twice, so we just broke even. We invested 2 molecules of ATP to get here. We just broke even by recovering that investment. I will point out that NADH is a useful molecule. We can take that to the electron transport chain in mitochondria, and we can get about 3 ATP for every NADH. But we've actually remade the 2 ATP molecules that we consumed in the beginning. The remaining steps are going to be about getting our another equivalent of ATP. So the next step is catalyzed by an enzyme called phosphoglycerate mutase. It's called mutase because it moves a functional group. This is an isomerization reaction. We start with the leaving group of the reaction above, 3-phosphoglycerate, and we're going to move the phosphoester from carbon 3, from the C3 hydroxyl to the C2 hydroxyl. That mechanism is somewhat complex. It involves a histidine side chain that already has a phosphate on it, and it's a series of SN2 mechanisms. I'm not going to require you to worry about that mechanism right now, but you do need to know that we're going to move the phosphate from C3 hydroxyl to C2 hydroxyl. So now we've got 2-phosphoglycerate. This is basically negligible change in free energy. The reaction's basically reversible. And we're getting close to the point where we'll be ready to generate our next equivalent of ATP. In the next step, here's 2-phosphoglycerate. We're going to convert it from 2-phosphoglycerate into a strange molecule called phosphoenol pyruvate. And the way we're going to do that is through an elimination reaction. If you look at 2-phosphoglycerate, like so many of the intermediates above, this is a beta hydroxycarbonyl compound. And beta hydroxycarbonyl compounds can eliminate to alpha beta unsaturated carbonyl compounds. And the mechanism for that, if you go back and look at chapter 24, is E1CB elimination. That is, we have a base, remove the alpha proton to give us the enolate intermediate. And then, so this first step is fast. And then the next step is slow. That is lone pair electrons on carbon 2, on alpha carbon 2, kick down and kick off OH minus as a leaving group. And that gives us, your product, which is an alpha beta unsaturated carbonyl compound, but the unusual part is that you've got the phosphate group connected to alpha carbon 2. This molecule is called phosphoenol pyruvate, and at that point we're almost done with glycolysis. At this point we're going to generate 2 new extra profit bonus molecules of ATP. Remember, we have 2 molecules of phosphoenol pyruvate for every molecule of glucose that goes through. So the mechanism is going to be SN2-like, as we did before. we're going to have the beta phosphoryl group of ADP attack this phosphate. Leaving group leaves. The leaving group can leave because the leaving group is an enolate, which probably picks up a proton as it's leaving. So that there generates your ATP, and then you have this molecule, and this molecule is an enol that can tautomerize to a more stable ketone. The ketone is more stable because carbon-oxygen pi bonds are lower in energy than carbon-carbon pi bonds. So tautomerization, sorry guys, I need to move some things over so we got enough space. Oh boy. Tautomerization from the enol to the keto form. And you've seen a tautomerization mechanism, so I'm not going to show you. You would first remove the proton from the enol oxygen. You would get an enolate that's resonance stabilized, and you would protonate it on carbon 3. And the product from that is pyruvate. And at that point, remember, we've gotten 2 molecules of ATP. We've broken glucose into 2 equivalent portions, and the final product, pyruvate, is ready to be brought into the mitochondria, where it can be further processed by something called the pyruvate dehydrogenase complex, which will ultimately convert pyruvate into acetyl-CoA. And we'll talk about that and the ensuing citric acid cycle next time. Until then, stay healthy, stay safe, and as Lord Voldemort always says, or for those of you who are not parcel tongues, or parcel mouths rather, stay organic.